Hello, and welcome to DAC 2024. I'm Troy Jones, System Architect for Codasip here in North America. I want to talk to you guys real quick about a demo that we have running for this show. It showcases our newly announced L110 embedded class RISC-V processor. It's a 3-stage embedded core that is specifically designed for low power, low area optimizations. So, demo that we have running here real quick is actually an AI inference, and let me talk to you about some of the details here to frame it. So basically what we're emulating or simulating, actually running in an FPGA, is collected sensor data from, let's say, an industrial system or an automotive system. As an example, what we're doing is we've collected audio samples to detect anomalies in, say, like a fan bearing or something like that, something that is preventive maintenance, right? This is something that is well known in industrial controls, automotive, for preventive maintenance. Okay, so what we've done is we have trained up an AI inference to detect anomalies in this audio source. So what do we have up here on the screen? Up here is a comparison of a standard off-the-shelf RISC-V core and an optimized L110. So here on the right side, we see an 80 megahertz clocked RISC-V core in the FPGA you see sitting here on the table. So in this particular implementation, we're running at about 1 inference per second. It takes about 78 million clock cycles per inference to calculate that, and it runs at about 1.6 millijoules per inference. Okay, so again, that is actually the Codasip L110 off the shelf. Just buy it straight from us, and that's kind of the performance you get in this particular example. So what did we do? We took that model, we profiled it using our Codasip Studio profiler and determined what methodologies we could use to improve performance. So there's some DSP going on, there is the AI calculations, matrix multiplies, things like that going on within this algorithm. So we figured out about 30-some custom instructions that we could implement to improve performance. So let's take a look at those numbers. So here we see that we are up by about 30%, 1.26, 1.3 inferences per second. Cycle count per inference dramatically dropped from about 80 down to 15 cycles per inference. And look at the power here. We're down to less than a quarter millijoule per inference. The one other feature I haven't pointed out that we were able to do is the original design was clocked at 80 megahertz. We dropped that clock frequency down by a factor of 4. We're running this only at 20 megahertz now in the same FPGA, and we're getting better performance at a fourth of the clock rate. So huge power savings advantages. So one of the things this demo is kind of cool about, we actually have a graphical representation of, let's say this is a battery powered implementation. All right, so down here on the bottom we have our optimized core in purple, and then this is the off-the-shelf vanilla L110, if we will. And then here the two green bars represent batteries. So this is the optimized battery, this is the vanilla off-the-shelf battery, and you can graphically see how much benefit you've achieved with battery life in this particular implementation. So there's a lot of details behind the scenes here on our using bounded customizations on our L110. Please stop by the show and look me up and ask me any questions you like. I can easily go into more specific details. So again, this really showcases the power of Codasip Studio and customizations on a RISC-V core. So thank you.